Welcome everyone. The outline of my presentation for day 3 includes memory allocation, contiguous and non-contiguous, algorithms for partitioned allocation, problems, paging, problems based on paging. Coming to memory allocation, it deals with allocation of partitions in main memory. There are two different types of memory allocation called contiguous and non-contiguous. Let us see the difference between both the types. Contiguous allocation allocates consecutive blocks of memory to a process, which means continuous memory blocks are allocated to a process. Non-contiguous memory allocation allocates separate blocks of memory to a process. Contiguous allocation is faster in execution, whereas non-contiguous allocation is slower in execution. Contiguous allocation increases memory wastage. Non-contiguous allocation increases memory utilization. Contiguous memory allocation includes single partition allocation and multi-partition allocation, whereas non-contiguous memory allocation includes paging and segmentation. These are all the differences between contiguous and non-contiguous memory allocation techniques. Under algorithms for partition allocation, we will see three popular algorithms called first fit, best fit and worst fit. First fit starts scanning empty partitions serially from the starting. When an empty partition that is big enough to store the process is found, then that partition is allocated to the process. Here the rule used is partition size must be greater than or equal to the process size. Coming to best fit, it scans all the empty partitions. Then it allocates the smallest size partition to the requesting process. Coming to worst fit, it scans all the empty partitions, then allocates the largest size partition to the process. So these are all the algorithms that come under partitioned allocation. Coming to problem solving, in the given problem, 6 memory partitions of 6 different sizes were given. These partitions must be allocated to 4 processes of different sizes. Let us see how the processes are allocated using first fit algorithm. Let me give the size of the given processes. Let me draw the memory partitions now. We need to divide these memory partitions into 6 different partitions of given sizes. And these are all the sizes of 6 different partitions. Usually, first fit algorithm starts for scanning empty partitions serially. And the rule used here is partition size must be greater than or equal to the process size. Now, the size of P1 is 357 KB. It must be allocated memory partition now. So, the algorithm starts scanning. First 200 KB will be scanned. 200 KB is not sufficient enough to hold P1 because the rule is not satisfied. Partition size must be greater than or equal to the process size. So here the rule is not satisfied. So the algorithm starts scanning the next free partition 400 KB. Here the rule is satisfied. 400 KB is sufficient enough to hold P1 because 400 KB is greater than 357 KB. So P1 will be placed here. Next P2. P2 needs 210 KB. The first fit algorithm again starts scanning empty partitions from the first. This serially. So 200 KB will be scanned first. 200 KB is not sufficient. Then the third partition will be scanned. Third partition is of 600 KB. 600 kb is sufficient enough to hold P2. So here P2 will be stored. Next P3. P3 needs 468 kb. Among the empty partitions, 200 kb is not sufficient enough. Then the algorithm scans 500 kb. 500 kb is enough to hold P3 because here the rule is satisfied. Partition size is greater than the process size. So here in this partition P3 will be stored. Then P4. P4 needs 491 kb. Among the empty partitions, 200 kb will be scanned, then 300 kb and finally 250 kb will be scanned. These partitions are not sufficient enough to hold P4, so P4 cannot be allocated memory partition. So this is how the processors are allocated memory partitions using first fit algorithm. Let us take the same problem and see how best fit algorithm allocates memory partitions. 4 different processes and memory partitions of 6 different sizes are represented as shown. Best fit algorithm allocates the smallest memory partition that is sufficient enough to hold the process. P1 needs 357 kb. 200 kb is not sufficient enough to store P1. The partitions that are greater than the size of P1 are 400 kb, 600 kb and 500 kb. So among these partitions, the smallest partition that is sufficient enough to hold P1 is the second partition. So here P1 will be accommodated. The size of P2 is 210 kb. It cannot be accommodated in the first partition. Among the other partitions, that is 600 kb, 500 kb, 300 kb and 250 kb, the smallest size partition that is sufficient enough to hold P2 is the last partition. So here P2 will be accommodated. Now P3 must be allocated memory partitions. Among 600 kb and 500 kb, the smallest partition that can hold P3 is 500 kb. So here P3 will be accommodated. The size of P4 is 491 kb. 491 kb cannot be accommodated in 200 kb or 300 kb. But in 600 kb, P4 can be allocated. So here in this partition, P4 will be accommodated. And this is how the memory partitions are allocated for the given processes using best fit algorithm. Let us see next problem. Again the same problem is taken. Let us see how worst fit algorithm works. Processes and memory partitions are represented as shown in the screen. P1 is equal to 357 kb. Among the 6 partitions, the greatest memory partition that can hold P1 is 600 kb. So here P1 will be stored. Next P2. The size of P2 is 210 kb. P2 cannot be allocated in 200 kb. But among 400, 500, 300 and 250, 500 kb is the largest. So P2 will be accommodated here. P3 needs 468 kb. Among the free memory partitions, that is 200 KB, 400 KB, 300 KB and 250 KB, these memory partitions cannot hold P3 since the size of P3 is greater. So P3 cannot be allocated memory partition. Likewise, P4 also cannot be allocated memory partition. So this is how worst fit algorithm works for the given problem. So in this problem, only P1 and P2 will be allocated memory partitions, whereas P3 and P4 cannot be allocated memory partitions since the memory partitions are not sufficient enough to hold P3 and P4. In this problem, 3 partitions are given and 3 processes are given of different sizes. We need to perform the allocation of processes using first fit, and also we need to find the internal fragmentation. Internal fragmentation is the type of memory waste that occurs if a process uses less space within allocated memory. It's a type of memory waste. Let me represent the given process and memory partitions as shown in the screen. Now, P1 needs memory partition. Using first fit algorithm, the algorithm scans empty partitions serially. So 200 KB will be scanned first. 200 KB is greater than 20 KB, that is the size of P1. Since the rule is satisfied, P1 will be allocated this partition. P2 needs 200 KB. The algorithm starts scanning. 700 KB will be scanned. 700 KB is greater than 200 KB. Condition is satisfied. So P2 will be placed here. And at last, P3 is equal to 50 KB. The algorithm scans. So the only available partition is 50 KB. Here the rule is satisfied. 50 KB is equal to 50 KB. So P3 will be accommodated here. This is how the memory partitions are allocated to the given processes using first fit algorithm. We need to compute internal fragmentation now. The internal fragmentation is a memory waste that occurs within the memory partition. And here comes the table that contains internal fragmentation computation for the given problem. The column header contains block size, process size and internal fragmentation. In the table, block size contains values 200 KB, 700 KB and 50 KB. They are nothing but the available memory partitions. Under process, P1, P2 and P3 are listed, and under internal fragmentation column, the memory wasted is calculated. Let me brief out how internal fragmentation is computed. The internal fragmentation for any process can be computed as block size minus process size. P1 is allocated in a block size of 200 KB and the size of P1 is 20 KB. Therefore, internal fragmentation is 200 KB minus 20 KB, which is equal to 180 KB. This is how internal fragmentation for P1 is calculated. Likewise, for P2, 700 minus 200 is equal to 500, which means that 500 KB memory is wasted. For P3, 50 KB minus 50 KB is equal to 0 KB. Hence, the internal fragmentation for P3 is 0 KB. From the table, total available memory is equal to 950 KB. That is, by adding all the available block sizes, we get the value as 950. Now, total internal fragmentation is equal to 180 KB plus 500 KB plus 0 KB. That is, just add all the values that come under internal fragmentation, which will be equal to 680 KB. So this is the total internal fragmentation value for the given problem. Let us see paging. Paging is a non-contiguous memory allocation technique that eliminates the need for contiguous memory allocation of physical memory. In this diagram, logical address space is divided into pages of equal sizes. Physical address space is divided into frames of equal sizes. Then page table is a data structure that performs the mapping of page number to a frame number. In the diagram, the logical memory contains 4 equal sized pages. The page table maps page number to frame number, and the first entry of the page table contains 0, 1. It means that page 0 is mapped to frame 1. Hence, in the physical memory, page 0 gets loaded in the frame 1. So this is the explanation for the given diagram. The logical address or virtual address is an address generated by the CPU. The logical address consists of 2 parts, and they are page number and page offset. Page offset can also be called as page size. The logical address space or virtual address space is nothing but set of all logical addresses generated for a program. Then physical address is an address that is actually available in the memory. Physical address consists of 2 parts, and they are frame number and frame offset or frame size. The physical address space is set of all physical addresses corresponding to logical addresses. Here let us see few formulae for solving problems that come under paging. For processes, virtual address space is equal to size of process. Then if we need to calculate the number of entries in a page table, then it can be calculated by the formula process size divided by page size. If process size is equal to 2 power x bytes, then the number of bits in virtual address is equal to x bits. This is x bits, not bytes. For main memory, physical address space is equal to size of main memory. Size of main memory can be calculated by multiplying total number of frames into page size. Then frame size is equal to page size. If size of main memory is equal to 2 power x bytes, then number of bits in physical address is equal to x bits. Another formula, if the address contains n bits and the memory is m byte addressable, then the size of memory can be calculated by using the formula 2 power n into m bytes. Let us see one example. If logical address is equal to 31 bits, then logical address space is equal to 2 GB. Let us see how 2 GB is arrived. The logical address space is usually written in terms of 2 power x. So this is equal to 2 power, the value for x is 31. 2 power 31. 2 power 31 can be written as 2 into 2 power 30. So 2 into 2 power 30, this 2 power 30 is nothing but 1 GB. So 2 into 1 GB is equal to 2 GB. This is how the calculation is arrived at. Another example, if physical address is equal to 22 bits, then physical address space is equal to 4 MB. Let us see how 4 MB is calculated. the address space is usually represented in terms of 2 power x bits. So here the value for x bits is 22. 2 power 22 can be written as 2 power 2 into 2 power 20. 2 power 2 is 4, then 2 power 20 is 1 MB, which is equal to 4 MB. So this is how the calculation is done. Using this formula, let us see how to solve problems that come under paging. In this problem, logical address space is given as 4 GB, physical address space is given as 64 MB, the page size is given as 4 KB. We need to find the number of pages, number of frames. Okay. Here, logical address space, in short I have represented as LAS. Logical address space is given as 4 GB. 4 can be represented as 2 power 2 into 1 GB can be represented as 2 power 30. So after simplification, we can write this as 2 power 32. If logical address space contains 2 power x bytes, then there are x bits in logical address. So number of bits in logical address is equal to 32 bits. We need to find number of pages. Number of pages is calculated by using the formula logical address space divided by page size. We have calculated the logical address space as 2 power 32. So divide 2 power 32 by 4 KB. Here 4 KB can be represented as, 4 is represented as 2 power 2, whereas 1 KB is represented as 2 power 10. So when we divide 2 power 32 divided by 2 power 12, we get the answer as 2 power 20. So this is the number of pages. This is the value for the number of pages. The physical address space is given as 64 MB. 64 can be represented as 2 power 6, whereas 1 MB is represented as 2 power 20. After simplification, we get 2 power 26. That is, since the bases are same, the powers can be added. So when we add the power 6 plus 20, we get 26. And this is how it is represented as 2 power 26. Therefore, the number of bits in physical address is nothing but 26 bits. Now we need to find the number of frames. Number of frames is equal to physical address space divided by frame size. See, in the given problem, the frame size is not given. But in the formula page, we have already saw that frame size is equal to page size. So we can put the value of page size for frame size here. So this is 2 power 26 divided by 2 power 12. Then the answer will be 2 power 14. Suppose if we are asked to find the number of bits in page number, let us see how to calculate. We know that the virtual address space is divided into two parts, page number and page offset. Page offset is also called as page size. We need to find the number of bits in page number. Okay. See, this is the logical address. This logical address is represented by using how many bits? 32 bits. We have calculated here. Page size is given as 4 KB. 4 KB is nothing but 2 power 12. So how many bits are used to represent this page size means 12 bits are used to represent. So here it is 12 bits. So page number, the bits used in page number can be calculated as 32 minus 12. So 32 minus 12 will be 20. Hence, if we are asked to find the number of bits used in page number, then we can use this procedure for calculating. So here 20 bits are used for page number. The physical address consists of two parts, frame number and frame size. We already know the number of bits used to represent the physical address. The number of bits used to represent the physical address is 26. Here we have calculated. Frame size is nothing but page size. We already know the number of bits used in page size is 12. So the number of bits used in frame number is 26 minus 12. 26 minus 12 is nothing but 14. So 14 bits are used to represent the frame number. So this is how the calculation is made. Let us move to the next problem. In this problem, a system with byte addressable memory is given. Byte addressable means in memory chip the data is stored as byte by byte. That's the meaning for byte addressable memory. 32-bit logical address, 4 KB page size and page table entries of 4 bytes each were given. We need to find the size of the page table. Let us see how to calculate. Given is number of bits in logical address, which is equal to 32 bits. Page size is equal to 4 KB. Size of one entry in the page table is equal to 4 bytes. We need to find the size of the page table. Size of the page table is computed using the formula number of entries in page table into size of page table entry. So number of entries in page table can be calculated by using the formula logical address space divided by page size. The number of bits in logical address is given as 32 bits. So therefore we can calculate the logical address space. Logical address space can be written as 2 power 32 and page size is 4 KB. 4 KB can be written as 2 power 12. So when we divide 2 power 32 by 2 power 12, we get the value as 2 power 20. Therefore, number of entries in page table is equal to 2 power 20. But we need to find the size of the page table. Size of the page table is equal to number of entries in page table, that is 2 power 20, into the page table entry size is given in the problem. It is given as 4 bytes. So multiply 2 power 20 into 4. So this is nothing but 4 MB because 2 power 20 is 1 MB. Hence 1 MB into 4 is equal to 4 MB. So this is how the calculation is done for the given problem. That's all for today's session. I request the faculty members to attend e-quiz once the link is shared in WhatsApp group. Thank you all.